when it really gets good, the engineers and the biologists or the surgeons or what have you can almost work hand in hand, because if you're doing it right, at the end, I can go back to the neuroscientists and say, our algorithm found this really interesting pattern that I think everybody missed. It's cool. It happens here and it happens here. Does that mean anything to you? And that can be a way of telling scientists, neurologists, whatever, some neuroscientists, something they hadn't noticed before.
Welcome to Owl Speak, where we discuss what's going on at the Temple College of Engineering. I'm your host, Casey Tinney, who will let you in behind the scenes with our Temple Engineering faculty, students, and alumni. Today, we're excited to welcome an associate professor in the Electrical and Computer Engineering Department, Dr. Iyad Obeid.
Hey, thanks for having me. It's good to be here.
You also have a secondary appointment in bioengineering, right?
I think so.
Okay. Okay. So some of your research focus includes neural and biomedical signal processing, applications for brain and computer interfaces, traumatic brain injury, virtual reality for cognitive and physical therapy, and neurofeedback. All that sound right?
I should probably try to focus on something. This is too many things.
Wide range of subjects.
Yes.
So you focus on machine learning and kind of how that plays a role in medical applications.
That's right.
Your research focus right now.
Yes.
Okay, so how did you get into that? So you have electrical and a bioengineering background. How did that work out?
So to go all the way to the beginning, when I was in high school, I discovered that there's electricity in our bodies, but instead of being carried with wires and electrons, it's managed with salts. So you have salts in your body like potassium and chloride and sodium, and anytime you have ions, or anytime you have salts in liquid, they become ions, and then anytime ions move, you have flow of current, and that's electricity.
Wow, okay.
Which is cool. And it turns out it's all over your body. So when your heart beats, you have you have muscle contraction, but that muscle contraction is controlled by these electrical signals that go throughout your heart and coordinate the heartbeat. And then it turns out in your brain, it's more or less the same thing, except instead of those electrical impulses causing a mechanical movement of muscle, it does things like contain information, manage your memories, and can send signals to your muscles and whatnot. I discovered that you have all these salts floating around in your body, and that sort of mediates your muscle movement, your cardiac activity, your thoughts, your learning, and so on. And I was fascinated by that concept. So I went to college and I studied electrical engineering, and I'm not really sure why I picked electrical, but I knew it was fun and I was enjoying my classes. And then in grad school, that's where I really went to learn about how to put all these things together. And I'm getting to the machine learning bit. It takes a second.
Yeah.
This is a long walk to get to that. So in grad school, I was staffed on a project that did brain-machine interfaces. And the idea behind those is that you want to be able to try to connect a brain to some sort of control apparatus. So the classic example is, let's say you have someone who is an amputee and they have a prosthetic limb and they'd like to be able to control that limb just by thinking about it. It doesn't have to necessarily be an amputee. It could also just be somebody with spinal cord injury who can't control their limbs, and you want to find a way for them to control their limbs just under the power of thought. So these are really fascinating problems, and 25 years ago when I got involved with them, it was very much a bit of a Wild West in terms of there wasn't a lot known, and there was a lot of cool, interesting new research being done. So if you want to make a brain-machine interface work, the basic idea is that you put a bunch of electrodes somewhere near the brain, and that somewhere is negotiable, right? Depending what kind of brain-machine interface you're doing, you can put wires directly within the brain, you can put them on the scalp surface.
Okay.
But you got to put them somewhere. You got to figure out, you got to listen to the brain. So that's step one. And then step two, which is where we start to get to machine learning, is you have to know what they're saying, right? Just because they're yelling at you, it doesn't mean you know what they're trying to say.
Yeah, you got to speak the language.
You got to speak the language.
Yeah.
That's right. So very quickly, the problem of how to build a good brain-machine interface turns into how well can you decode the neural signal,
Okay.
which is something we still don't know an awful lot about. We're getting better, but it's still unknown more than it is known. So the basic idea is whatever you're using for your listening, you set that up, and you say, okay, we're going to listen to the brain while I instruct you to think about moving your hand out straight.
Okay.
So you move your hand straight forward, and we make a bunch of recordings of that. And then we say, great, now let's do the same thing, but move your hand to the right, move your hand to the left. And so what we try to do is you build up a catalog. You say, every time you think about moving your hand in this direction, this is what I see. Every time you move your hand in that direction, this is what I see.
Okay.
And so that's effectively your attempt to understand to decode the language of the brain.
Okay.
It's not like really speaking the brain's language, but it's a pattern recognition task. So it's very hard to predict. From that, you can do things like say, okay, well, now I know what to look for. If I see XYZ pattern, I'm probably sure that you're moving your hand to the left. Okay, so then you can stimulate or control a prosthetic or whatever it is. You can move the hand to the left. You don't really know what the language is, but you can make a correlation between, okay. As the game gets more sophisticated, or as the study of brain-machine interfaces gets more interesting, you can start to take that to new levels. So, for example, you might have figured out the patterns for left, right, backwards, and forwards, but you don't know what up is. And the reason you don't know what up is you don't speak the language, right? You're just sort of like mimicking. You're learning to recognize patterns that you've already seen before, but you can't predict new patterns.
Okay.
Because you don't speak the language.
Yeah.
Right. So that's where machine learning really gets interesting, because whereas 25 years ago, we had relatively limited ability to build mathematical models, they were pretty good at predicting things based on stuff it had already seen before, but it wasn't really good at predicting things that it hadn't seen yet. We just didn't have the tools for that. We didn't have the computers that were powerful enough to figure all this out. We didn't have the raw data. I mean, you just need like tons and tons and tons of data.
Yeah.
And we didn't really have the algorithms. There weren't all these really cool machine learning algorithms the way they are now. So what's fun about what's changed now is that all of those limitations are less of a problem than they used to be. There's a lot more people doing this kind of research. So there's a lot more data that's available, and there's a lot more of a culture of making data available. And then there's a lot of really cool machine learning for trying to suss out these things, these patterns, and make predictions in the future. So the way I would invite you to think about this is to say, you want to learn a foreign language. Like, let's say you want to learn Japanese, something that's like really not on your radar. Yeah. Right? So you go to Japan, and you very quickly learn how to say, I'm hungry or I'm thirsty, because you can make some hand gestures and you figure that out, and somebody tells you what those things are. So you can tell someone you're hungry, you can tell someone you're thirsty, but you can't tell them you're tired, because you don't understand the language. Yeah. So in essence, what we're trying to do is we're trying to record all these different audio clips of people speaking Japanese, and then look for patterns in the language and say, okay, based on the little bit that we know and based on the patterns that we can suss out from the data, can we predict what it means to say I'm tired? And that's effectively what we're trying to do with decoding brain signals. Okay. So you're trying to predict what's going on if we're comparing it to the language, trying to predict what someone's going to say without knowing the vocabulary word. That's exactly right. Say. Okay. Yeah. So that's what's interesting about all this brain decoding stuff, is that no one really knows the vocabulary super well. You can work out, this fragment means I'm hungry or I'm thirsty or whatever, but you don't really know that there's grammar. You don't know that there's individual words in there. Okay. It's just like a lump. Something that I'm thinking of when you're talking about this, and forgive me if this is
a not correct application, but I feel like I've heard of when they're doing brain surgery and someone like plays a musical instrument during the brain surgery to see which parts of the brain
Isn't that fun?
like activate.
Yes.
Because they don't know until they go in and see it. You can't predict it.
That's a little bit different, but
Okay.
not crazy different. In that instance, what they're doing is the regions of the brain that control specific things can be incredibly small.
Okay.
So sometimes there'll be a brain surgery where it's necessary to remove a tumor. So that involves taking away a little bit of brain tissue. Or it might be necessary to ablate or burn off a little piece of brain tissue, let's say if it's causing a seizure or something. So, of course, you want to do this as precisely as possible because you want to fix what needs fixing and nothing else.
Yeah, you don't want to mess with the brain too
You don't want to
much.
mess with the brain, right? So the way that they do that is they put these. You do what you can ahead of time. So they map surgically. They'll do an MRI. They'll do whatever. And they get these pretty sophisticated maps where they can tell fairly closely within a millimeter or so which part of the brain that they're targeting. But when they actually go to do the surgery, they want to make sure that they are actually at the exact right pinpoint. So then they actually put electrodes deep in the brain and they say, okay, play the violin. Am I recording anything here? No. Okay, so this is not the violin part of the brain.
Okay.
We can operate here.
Does that also play a role in why it's so difficult? Is that the parts of the brain that control certain things, like you said, are so small? Does that also
Absolutely
play a role in the machine learning aspect of it?
It plays, and it does play a role. And actually that feeds in very nicely your point about the smallness. It feeds into the other problem, which is that the things that you're trying to listen to are very small, and the tools that you're using to record from them are comparatively enormous, right? So when if you've ever seen somebody get an EEG and you put a scalp electrode on the scalp, that electrode might be, let's say, 1 centimeter in diameter, which doesn't seem very big, but compared to the size of a neuron, it's enormous. And it's really far away. Again, comparatively speaking, it's listening through hair, skin, bone. You've got membranes covering the brain, and then that just gets you to the surface of the brain. The part that you might be interested in listening to or diagnosing or whatever might be a structure that's buried within the brain. So you're using a really imprecise tool to make a recording from very far away. And like you were saying, the things that you're looking for, trying to be listening to, could be tiny. And it doesn't get a heck of a lot better when you stick even if you say, okay, fine, I'll stick an electrode in the brain, it's still a blunt instrument.
Wow. Okay. So you go through, you do the whole operation, and it's still not perfect.
Yeah.
Wow. Okay.
So what's wild with brain-computer interfaces, this is less to do with machine learning, but the really fun part about it is that the brain can adapt to make use of your interface.
Wow.
So for example, you put electrodes in the brain that you're hoping are going to be listening to the motor control part. So let's say you want to control an arm, so you know roughly where the brain regions are for controlling your right arm movement. So you put a bunch of electrodes in there and you start to listen to them and you try to map out their vocabulary, and it sort of works. Now, it sort of works because you might have not gotten exactly a very good population of cells, or maybe they're not exactly the cells that control arm movement. But what's wild is that if you keep at it day in and day out and you practice, eventually those cells can repurpose themselves.
Wow.
Right? So they say,
so crazy.
Subconsciously, they can just say, oh, if we could make ourselves be the cells that control arm movement, then we could pick up this mug. And you give it long enough and it gets better.
It's crazy. I mean, they say the brain's a muscle, but I didn't know it could completely change its function.
It's wild. So there's all
crazy.
these really cool experiments, and they figure this out early on. You can have monkeys. The classical experiment is you put a dot on the screen, and then the monkey controls a cursor, and they try to think the cursor to move onto the target. And you set this up in the beginning. They don't do very well at this game. They perform quite poorly, but over time, as they rewire their cells, they get better and better and better at it. And you can actually look at the cells that they're measuring, and they're their behavior changes over the course of weeks until they can get really, really good at targeting at moving the cursor to the target.
That is absolutely
it's
insane.
So cool.
It's
yeah, our brains are amazing.
So you're talking about the machine interface part of it, and recognizing patterns and predicting patterns. And what my brain is going to is AI. It's a very hot topic right now.
That's right.
Does AI have a role in this?
Absolutely.
Okay.
I mean, so at its best, what artificial intelligence does is find patterns in data that you didn't know were there.
Okay.
All right. So, for example, another thing that we spend time on in our lab is trying to look at pathology slides and find cancerous cells in pathology slides. So a nice way to think about it is you can, when a pathologist trains to become a pathologist, they look at, I don't know, tens of thousands of slides throughout their training, and they learn over time that this little red blob is unusual in this type of cell, and it's too big and it's irregular, or whatever the criteria is, and that's probably cancerous, right? So they learn what to look for. In artificial intelligence, you can take 10,000 slides that have cancer and 10,000 slides that don't have cancer, and you feed them into a computer and you say, you figure out what's different. And you're not telling it to look for irregular shaped blobs. You're not telling it to look for things of a certain size or color or whatever. It looks for the patterns for you, and then it learns how to segment the patterns. And so you can take that same idea and apply it to decoding brain signals, right? We talked earlier about not knowing the vocabulary. Well, again, if you can collect enough data and feed it into a computer with a big enough algorithm, the computer can notice patterns. You say, look, we see this type of brain activity. We're seeing it in a bunch of different areas or in a bunch of different contexts. I wonder if it's significant, or I wonder if it means something. So that's, at its best, how AI is powerful, because it can suss out these patterns that may be even invisible to the human eye. It can find them and suggest that they are meaningful.
Wow. Wild. All of it's wild.
It really is cool. And at its most fun, what I love about this branch of engineering is that when it really gets good, the engineers and the biologists or the surgeons or what have you can almost work hand in hand, because if you're doing it right, at the end, I can go back to the neuroscientists and say, our algorithm found this really interesting pattern that I think everybody missed. It's cool. It happens here and it happens here. Does that mean anything to you? And that can be a way of telling scientists, neurologists, whatever, some neuroscientists, something they hadn't noticed before. And that can become the basis for new discovery or new hypotheses or what have you.
Okay.
Yeah.
It's kind of merging all the fields.
Right.
Together.
The field is sort of circular in a way.
Yeah.
So we're not, it becomes more about a collaborative research effort than it does just us trying to, just kind of go on our own and we're not trying to outdo the neuroscientists, right? We're all part of the team.
Yeah,
right? We're all
everyone.
trying to, right. It's just another tool for figuring out how the brain works or how pathology works or what have you.
Yeah, everyone, when you work together, I feel like you find out more with the different
You find out
fields.
more. That's exactly right.
So what are some specific projects you're working on with this? Because we talked a lot about, measuring. Are you physically doing the data now where it's like you tell the arm to move up, tell the arm to move left and right? Or what are you working on now with this?
So that the stuff with the moving the arms, I haven't messed with that in a very long time.
Okay.
That was work I did when I was in grad school, and that requires a very specific lab setup, which I have no interest in trying to duplicate at Temple. What I am working on now is I have some collaborators at Jefferson Hospital, and we are attempting to, same kind of problem where we're interested in figuring out how to communicate information with brain cells, but instead of doing it writ large in the brain as a whole. We're trying to do it with a little cluster of cells in a petri dish.
Okay, very interesting.
It is very right. So it's the same idea. You know, sometimes in science, you want to look at the whole system because it's the whole system, right?
Yeah.
And sometimes the whole system is too complicated. You're like, well, what if we could just break it down to its finest grain bits and understand that, and then work up to the big thing that we didn't understand? And you need people kind of looking at it, the big picture and the little picture. So we're working on a project. We're working with the little picture.
Okay.
And so we have these little petri dishes, and we're clustering. We're growing cells in those dishes, brain cells.
Okay.
And we are trying to crack the code of how can we send information to those cells in a way that it means something to them. And then, so for example, let me put some depth into this so it's not just theoretical. So let's say if I ask you to do a task, something very trivial like, can you tell apart a circle from a triangle?
Okay.
Right? We could train a very small child to do that. It's not hard. Okay. But then you can make it interesting, right? So you could say, well, what if the circle was partially occluded? You know, like if I cover up half the circle, you can still tell it's a circle. Even though it's not actually a circle, you can infer that it's a circle, right? And with a triangle, same thing. I can cover up bits of it. You can infer it's a triangle, or I can rotate it, or change its size, or its color, or whatever, and you still know it's a triangle.
Yeah.
Okay. So what we're trying to do is we're trying to do a series of experiments where you take a blob of cells, and I want to show it a circle. So how do you do that? First of all, we're not really sure.
Yeah.
But the idea is you make these little electrical stimulations. So you say, okay, here's a circle. Circle's got an outline. Maybe, and in your petri dish, you've got a grid of little electrodes where you can stimulate the electrodes. So you say, okay, what if I stimulate those electrodes in a circle, and then I measure the response of the dish? Okay, maybe every time I show it a circle, I get some kind of response. And then every time I stimulate the electrodes in the shape of a triangle, I get a different response. So you look at those, you provide it with a bunch of stimuli, you look at responses. You take that triangle, you say, what if I rotate it a little bit? So instead of creating a triangle shape pointing one way, I'll stimulate electrodes in a different pattern with a triangle rotated a little bit or missized. Okay. In theory, it should change a little bit, not a lot, because it's still a triangle, but maybe it's rotated a little bit.
Yeah.
So you try to figure out what's similar, what's different. The bits that are similar should be the things that say, I'm a triangle and not a circle. And the things that are different should be, oh, you rotated this triangle a little bit, or you reduced its size, or you increased its size, or whatever it is.
Okay.
So the idea is you look at those, you put it in a little dish. It's very easy to access you can listen to every neuron. You can stimulate every neuron. You have like a really high degree of control over what's being said, what's being recorded, what's being listened to. And you can try to suss out patterns in a way that would be unrealistic in a brain that's got 1 billion neurons in it.
Okay,
and
so you can focus,
1 trillion synapses.
Focus on like a smaller
That's exactly
population.
right, yeah.
Okay.
So we're working on stuff like that. The idea is to be able to, if you really want to get meta for a moment.
Why not?
Why not? So we're talking about machine learning and artificial intelligence. Those are techniques that model human thought or human thinking, right? Humans are very good at looking for patterns. That's basically what machine learning is a computerized system of looking for patterns. And computers are really good at this, but they're very inefficient at doing this.
Okay.
Let me explain. Our brains, to do their job, use about 10 to 12 watts of power. It's barely enough to run a coffee machine.
Okay.
Right? And with that amount of power, you can figure it out fairly easily, right? If you figure out how many calories you consume in a day, you convert that into joules, you figure out 20% of it is for running your brain, you do all the math, it comes out to not very much power. Okay. So for a supercomputer to tell the difference between a circle and a triangle requires like enough electricity to run a village.
Yeah. Okay. Okay. When you put it that way.
So
Got
on a
it.
per watt basis, our brains are insanely efficient
Yeah.
at looking for patterns. Okay. So there's this concept that the way forward for computing is the things that computers are good at should be done by computers. So things like adding and subtracting numbers, sorting. There's certain tasks that computers were built to do that they're insanely good at.
Yeah.
And then there's things that computers can do but are very inefficient at, which is looking for patterns.
Okay.
Okay. So wouldn't it be fun if you could build a computing platform where some tasks were handled by a bunch of transistors, being a computer, and a bunch of other tasks were handled by neurons in a dish that could...
Wow. Okay.
Right?
Okay. Wow.
Right. So the idea is like, the tasks come in and you've got some processor that says, oh, this is a sorting task. Send it to the sorting algorithm in the transistors. And then you get another task, which is, oh, this is a pattern recognition task. Send it to the neurons. Wow. And if you had a way of communicating with those neurons, sending it information reliably, and then getting the information back from it and interpreting it, you could have a really efficient way of doing certain kinds of computing that conventional computers will never be efficient at. You can make them more efficient, but they're never going to be as efficient as a neuron. It's like the perfect pattern recognition device.
Wow. Okay.
Yes.
I'm also now getting when people talk about how like cryptocurrency is really bad for the environment, and you're kind of like, I don't understand how that works. I kind of the amount of power it takes for a computer to do all this.
Computers are amazing, but they're computationally expensive, right? They take a lot of power. And that's what makes our phones a miracle. I mean, the fact that your phone can do what it does on the power budget that it gets away with is breathtaking. But a lot of that it achieves by pushing some of the bigger computing tasks into the cloud.
Yeah.
So a lot of things, you're just looking at the results of some massive
warehouse
operation that's been done right in a warehouse somewhere.
Okay.
It's changing. Phones are always becoming more powerful, and their transistors are always becoming more efficient. That's like a whole different branch of engineering that you should probably have somebody more competent than me come explain to you. Computers are powerful but very power inefficient.
Wow. So that's so interesting to hear. You talk about how AI is becoming like not human-like, but doing tasks that we thought a computer couldn't do, like writing a pilot or something like that.
Yeah.
And then when you compare it to the amount of energy it takes and how like one day they could be combined, it's both scary and really cool at the same time.
It kind of goes round and round in circles. Yeah. I mean, if you get philosophical about it, you say, well, the computer can write a script, but it's very cost inefficient. What if we could make a bunch of cells that could write a script for you instead? And you say, well, we kind of already have that. That's us.
Yeah.
Right.
Yeah.
So, it's like a dog chasing its own tail at some point. It becomes a little bit of circular logic. And I don't really pretend to know where all that's going to end, but it's certainly interesting.
Wow. Definitely. So you're working with collaborators at Jefferson. How long have you guys been working on this?
A couple years now.
Okay.
We have I have a grad student that kind of sits there permanently, and I'm close with the rest of the team there. So we do a lot of the number crunching, and there's also turns out a fair amount of fairly low level engineering, like electrical engineering, that has to get done, right? So you have to grow neurons in a dish, and that dish has to be able to have electrodes in it that can record and stimulate those neurons. And some of that stuff you can buy off the shelf, but then all of it needs to be kind of customized and tweaked. So we spend a lot of time doing fairly mundane, but technically fascinating tasks. Is the stimulation working properly? If I stimulate in point A, does that also stimulate point B, even though I don't want it to stimulate point B? Like, can I localize my stimuli? So you have to solve a lot of really like low-level technical problems in order to get good science out of it. Otherwise, it turns into a big soupy mess, which benefits nobody.
Yeah. So in terms of, you've been working on it for a couple of years, where do you see this specific project going? Are you hoping to get it published and then have some more people focused in AI take it from there to do the neuron computer thing, or are you hoping to have this experiment evolve over time?
I'd like to see it evolve. I think it's really interesting. One of the mind-bending parts about this field is that there's a lot of different applications for it. So one of the things that's fun is that there's a basic science application, right? I just want to know how the brain works. I just want to know how we communicate information. And if that's all I ever get out of this, that's valuable. So that's one way you could think about it. Okay. Another way you could think about it is, if I understand how the brain works, I could make an efficient computer. That's an application. Or if I understand how the brain works, I could make a brain-computer interface and help augment the lives of people that need it. So, and I can't do all of those things. I mean, I can't even do one of those things by myself, right?
Yeah, yeah.
So, I mean, how do I'd love to see, obviously all this is going to get published as we go. That kind of work is low level enough that I feel that is mostly going to be fundamental, like basic science work. But I would love it if we had collaborators that could work with us to figure out how to actually build a computer with two halves to it, a biological half and a transistor half. I mean, that would be, I could retire off of that. That would be so much fun.
Yeah.
But there's a lot of cool ways it could go. And I think part of the realities of being a researcher are that you have to accept that you can't get to everything. Yeah. Because the world is big, the problems are complicated. I mean, there's only so much you can drill down into so many different things before you run out of time or energy or mental bandwidth or what have you. But I'd love to stick around and see this turn into a computer that can have the two parts to it. Would be fascinating to me.
Yeah, I mean, like you said, the field is kind of circular, so it's like bringing in everyone with their different specialties to figure out where this can go.
Yeah, that's exactly right.
So exciting.
Yeah.
I think also I'll move it a little more to students and kind of learning about engineering. Is you started in electrical engineering, and I think, we have all our different silos at the College of Engineering. What's your advice to students when they're interested in multiple things? How can you combine all those things?
That's a good question. Well, as a student, I'm sure any student who hears me say this will roll their eyes, but your biggest asset as a student is your time, right? So you're young, relatively speaking, you probably have fewer responsibilities than you might have later in life, although I know that's not true for everybody. But, my advice would be use that time wisely to read and get involved with things online or go to visit people's labs. Expose yourself to as many things as possible, and it will always bear fruit, even if tangentially or whatnot. And I'll give you an example. When I was in college, through a series of really bizarre coincidences, I wound up learning a bunch of geology and going and spending a few months camping in the desert of Death Valley and like Southwest United States, learning how to measure rocks.
That's so cool.
And read terrain maps, and on these like giant expeditions with like 50 different geologists. And I mean, I was just tagging along, and it was super tangential, but I feel like it's enriched me. It's certainly not directly in any way that I apply to my day-to-day science, but it's enriched me in ways I would never take back. It was certainly a good use of time, which is really like your number one asset when you're young. So, I mean, the less rambling answer to your question is, obviously pick a major, get good at it, right? You need to have a primary foundation for your professional development. So whatever your major is, take it seriously and get really good at it. But find time to read, to expose yourself to other things. I mean, even if it's just watching videos, like there's so much good content online. Yeah. But we're at a university, right? You can go to a talk every day from some noted expert if you're willing to look online and see the lecture schedules of all the different departments. Like, no one's going to tell you can't go listen to a psychology lecture or a computer science lecture or a math lecture. And I go to those things from time to time, and sometimes I'll walk away and say, I really didn't understand most of that. It was really interesting. So yeah, I mean, that's what you do, is just expose yourself to as many things as possible. If you really love something, you can sort of pester a professor and see if you can get to be part of a research project, even if it's something as mundane as washing beakers. That's always the example I use, is like, you're going to be the person that washes the beakers. That's fine. Like, you're still gonna learn something, right? You're still going to look over your shoulder and see what the grad student is doing, or the whatever, and you'll learn something. And if you're good at washing beakers, maybe they'll ask you to come do something a little bit more consequential. But just be curious, right?
Yeah.
I think having that innate sense of curiosity will lead you to things that you're passionate about. Certainly, that's one of my favorite things about being at a university, is that there's so many cool things to go poke your nose in and just kind of learn and try to broaden your horizons. It's just go to the library and walk around. I mean, it's full of books and they're all interesting, right?
Definitely.
So yeah, just be curious.
Definitely very good advice for engineering students who I feel like are always interested in multiple things.
I know, and what's crazy is there's so many things. I think that's part of the paralyzing thing, is there's so many things to be interested in, right? Like, you can't possibly be good at all of them. You can't possibly digest all of them. But yeah, that's, so maybe it's not the best, maybe it's not realistic advice, but I don't know, it's what worked for me. Just be open to new experiences and go chase things down when they're interesting to you. And, everything's a learning experience in the long run.
Definitely.
Yeah.
Everything's a learning experience. I feel like maybe they'll take that away from this. Well, thank you, Dr. Obeid, for coming in. Is there anything else you wanted to cover? Anything we missed?
I don't think so. It's been a pleasure to be here. I'm new to the podcasting game, but
all of us are. Everyone in this room is new to the podcasting game.
Yeah. No, just brains are big, awesome, beautiful, messy, complicated. No one really understands them. They may be beyond understanding. I mean, that's what's really, there's these theories of physics where there's like Newtonian physics, where we understand things at a macro level, and then there's quantum physics where we understand things at a very small level. And in theory, it's all the same matter. All right. In theory, the physics is all the same, but there's no unified theory there's no one theory that gives you the Newtonian mechanics and the quantum mechanics all under one roof. And I feel like the brain is going to be the same way, right? Yeah. Where it's such a complicated beast that there's going to be all these different theories that sort of work for individual bits of it, but it's going to be very hard to consolidate under one kind of umbrella. At least certainly within my lifetime, it's that complicated. But if we can chip away at a little piece of it, if nothing else, it's fun.
Yeah, that's true. If nothing
Whether or not it's
fun.
Useful, I don't know, but
we'll find out.
We'll find out.
Well, I mean, a great way to look at it, and thank you so much for sharing your research. It was very interesting. Thanks so much, Dr. Obeid, for joining us.
Thanks so much. Appreciate it.